Hello, and welcome to Space for Sleep. Uranus looks quiet only because we have barely seen it. From a distance, it appears almost featureless. A pale blue-green sphere far beyond Saturn, smooth enough to seem simple, cold enough to seem inactive, and remote enough that even many astronomy books treat it like a brief stop on the way to Neptune. But that calm appearance is misleading. Uranus is one of the strangest planetary systems we know. It is the planet that rotates almost on its side. Its seasons last more than 20 years each. Its magnetic field is tilted so far from its rotation axis that the whole magnetosphere tumbles through space like a broken compass. Its atmosphere is colder than Neptune's in places, even though Neptune is farther from the Sun. Its internal heat is almost missing or trapped so deeply that it cannot easily escape. Its rings are dark and narrow. Its moons carry cliffs, canyons, possible ancient oceans, and surfaces that Voyager 2 only partly revealed. Uranus is not boring. It is underexplored. That is the real subject of this story. A planet that appears calm because our view of it is incomplete, and a world whose quiet surface hides some of the most important unanswered questions in planetary science. Only one spacecraft has ever visited Uranus. Voyager 2 passed by in January 1986, during a brief encounter that gave us a first close look at the planet, its rings, its magnetic field, and its moons. Then the spacecraft moved on toward Neptune, and Uranus was left behind for nearly 4 decades. Everything since then has come from Earth-based telescopes, Hubble, Webb, and mathematical models trying to extract meaning from a distant blue-green disk. That single flyby was enough to show that Uranus was not the simple planet it seemed to be. But it was not enough to explain it. The first mistake people make with Uranus is assuming that a smooth planet is a simple planet. Smoothness can mean calm, but it can also mean distance. It can mean that the cloud patterns are hidden at wavelengths our eyes do not see. It can mean that the best spacecraft image was taken in the wrong season. It can mean that the interesting physics is not painted clearly on the top of the atmosphere, but buried in the magnetic field, the heat budget, the moon system, and the deep interior. For a viewer, Uranus has the opposite problem from Saturn. Saturn explains itself visually. Its rings make the case before anyone says a word. Uranus does not. Uranus asks for attention before it rewards it. But once the questions are visible, the planet becomes difficult to dismiss. Why is it sideways? Why is its atmosphere so cold? Why does it release so little internal heat? Why is its magnetic field not just tilted but displaced? Why do its moons show signs of geological complexity when most of them are too small to be so interesting? Why has the next flagship mission priority been given to a planet most people barely think about? Those questions are the reason Uranus matters. William Herschel was a musician. That fact is worth stating plainly, because the discovery of Uranus is sometimes told as a story of pure professional astronomy when it was, at least at its origin, something more unusual than that. Herschel was born in Hanover in 1738, trained as an oboist in the Hanoverian Guard, emigrated to England in his early 20s, and spent the first several decades of his adult life as an organist and music teacher in Bath. Astronomy was his hobby, an intense, consuming, ultimately life-changing hobby, but a hobby. He taught himself telescope making in the 1770s, constructing increasingly large instruments of his own design and manufacture, and he began a systematic program of surveying the sky, not searching for new discoveries in particular, but cataloging the heavens with a thoroughness that was unusual for the time. Herschel's approach to astronomy was methodical and exhaustive in a way that professional astronomers of the era, constrained by the specific observational programs of their institutions, rarely matched. He was, in effect, doing a comprehensive census of the sky, examining every patch of it, recording every unusual object, building up a picture of the sky's contents rather than focusing narrowly on specific targets of interest. It was this systematic, comprehensive approach, rather than any specific hunt for new planets, that placed the new planet directly in his field of view on the night of March 13, 1781. The object appeared as a small disk, circular, with measurable angular size, rather than a point of light. Stars are so distant that they appear as points regardless of the magnification used. Only objects in the solar system, close enough to resolve into an actual disk, show any apparent size through a telescope. Herschel noted the observation, returned to it on subsequent nights, and observed that it was moving relative to the stars, another sure sign of a nearby solar system object rather than a star. His initial conclusion, announced to the Royal Society, was that he had discovered a comet. The conclusion was wrong, but the discovery was right. Other astronomers observed the object and found that its orbit was not cometary but planetary, nearly circular rather than highly elliptical, consistent with a planet rather than a comet. The orbital calculations confirmed it. This was a new planet, orbiting the Sun at a distance of nearly 20 astronomical units, far beyond Saturn, completely unknown to all previous astronomy. Herschel had discovered the first new planet in human history, the first planet found that was not visible to the naked eye, the first detected through instrumentation rather than natural observation. There is a historical footnote worth including here. Uranus had in fact been observed before Herschel's discovery. It had simply not been recognized as a planet. John Flamsteed, the first astronomer royal, had observed and catalogued the object in 1690, recording it as a star designated 34 Tauri. Subsequent observers, including Pierre-Charles Le Monnier, had observed it at least a dozen times between 1750 and 1769 without recognizing it as a moving object. The observations were there in the historical record, but the interpretation, the recognition that what appeared to be a star was in fact a nearby planet slowly moving against the background, required someone to be looking with Herschel's systematic attention and to notice the telltale disk shape that distinguished a nearby object from a distant star. The naming of the new planet generated significant controversy. Herschel himself suggested Georgium Sidus, George's star, in honor of King George III, who rewarded him handsomely for the discovery and appointed him king's astronomer with an annual stipend that allowed him to leave music teaching and dedicate himself entirely to astronomy. This name was used in England for some decades, but was rejected internationally as too parochial and not in keeping with the mythological naming tradition of the other planets. Other names were proposed, including Herschel after the discoverer, a sensible idea that was similarly rejected for lacking mythological continuity. The German astronomer Johann Elert Bode suggested Uranus, after the ancient Greek god of the sky, father of Saturn and grandfather of Jupiter, fitting the generational pattern of the planetary names. This name was slowly adopted over the following decades and became universal by the mid-19th century. It is worth pausing to consider what the discovery of Uranus meant for the state of human knowledge at the time. The solar system had contained, in the collective human understanding, 6 planets from time immemorial: Mercury, Venus, Earth, Mars, Jupiter, Saturn. These were the planets of the ancient world, the planets that had shaped mythology and astrology and the early history of astronomy. Their existence was simply part of the fabric of understood reality, as assumed and unquestioned as the existence of the continents. The discovery of a 7th planet was not merely adding an item to a list. It was shattering the assumption that the list was complete, demonstrating that the solar system was larger and contained more than anyone had imagined, and implicitly raising the question of whether there might be more to find. The discovery of Neptune 65 years later, and then Pluto in 1930, and then the recognition of the Kuiper Belt and its population of dwarf planets, all flow from the conceptual revolution that Herschel's discovery inaugurated. The discovery also transformed Herschel's life and, more broadly, transformed human understanding of the solar system's scale. Before 1781, Saturn was the outermost known planet, and the solar system seemed to end at Saturn's orbit, roughly 10 times Earth's orbital distance. With Uranus at 20 astronomical units, the known solar system doubled in size overnight. The reaction to the discovery, both in scientific circles and among the educated public, was something like what discovery of a major exoplanet system might produce today. A shock of expanded scale, a realization that the universe was larger than assumed, a sudden extension of the frontier. There is another reason Herschel's discovery still matters. Uranus was not merely a new object. It was the first time human beings learned, in a practical and undeniable way, that the architecture of the solar system could extend beyond the limits of ancient sight. Before Uranus, the boundary of the known planetary system had been Saturn. Saturn was slow, remote, ringed, and mythologically old. It felt like an outer wall. Uranus broke that wall. After Uranus, it became reasonable to ask whether there were still more planets. The discovery changed the mental habit of astronomy. The sky was no longer a finished inventory inherited from antiquity. It was a place where large things could still be hidden, not because they were invisible in principle, but because no one had yet looked carefully enough, long enough, or with the right instruments. That shift matters because it set the stage for Neptune. The discovery of Uranus expanded the solar system. The later irregularities in Uranus's orbit helped reveal Neptune. In that sense, Uranus was both a discovery and a tool of discovery. It did not simply add one planet. It made the outer solar system intellectually unstable in the best possible way. It suggested that the known map was provisional. This is a recurring theme in planetary science. A world appears as one thing at first, a point of light, a smooth disk, a simple category. Then better instruments arrive, and the object becomes more complicated. Uranus followed that pattern from the beginning. It was first mistaken for a comet, then accepted as a planet, then treated for a long time as a distant pale sphere, then revealed by Voyager as a sideways ice giant with a bizarre magnetic field and a moon system full of geological surprises. The history of Uranus is the history of an object repeatedly becoming stranger as it becomes better known. Caroline Herschel's role is also worth remembering because the story of Uranus is not only the story of one man looking through a telescope. Caroline assisted William in his observations, took notes, organized records, and carried out her own independent searches. She became the first woman in Britain to receive a salary for scientific work and discovered comets in her own right. The Herschel household was not a modern observatory in the institutional sense. It was a workshop, a music room, a telescope factory, an archive, and a scientific engine built around relentless observation. That matters because Uranus was discovered through method. It was not found because Herschel looked once and got lucky in the simplest sense. Luck put the planet in the field of view, but preparation made the discovery possible. He had built instruments good enough to show the disk. He had trained himself to recognize subtle differences. He had committed to surveying the sky systematically enough that an object others had logged as a star became something suspicious. Many discoveries work this way. The moment looks sudden, but the suddenness rests on years of attention. Herschel went on to have an extraordinary scientific career. He discovered Uranus's two largest moons, Titania and Oberon, in 1787. He discovered two of Saturn's moons, Mimas and Enceladus, in 1789. He conducted extensive studies of binary star systems, nebulae, and what he called island universes, what we would now call galaxies. He proposed the structure of the Milky Way from systematic star counts. He He discovered infrared radiation by splitting sunlight through a prism and finding that a thermometer placed beyond the red end of the spectrum registered a rise in temperature. His sister Caroline Herschel, who worked closely with him, discovered 8 comets and was one of the first women to receive an official scientific salary in Britain. William Herschel died in 1822, and the planet he discovered has been rolling sideways through the outer solar system for the billions of years before and after his brief, precise encounter with it. Uranus orbits the Sun at an average distance of about 19.2 astronomical units, roughly 19 times farther from the Sun than Earth. In kilometers, that's approximately 2.9 billion kilometers. At that distance, light from the Sun takes about 2 hours and 40 minutes to reach Uranus, and the sunlight arriving there is only about 1/369th as intense as what we receive on Earth. The Sun from Uranus's cloud tops would appear as a brilliant but distant point, significantly smaller than it appears from Earth, far too dim to provide significant warmth. Uranus takes approximately 84 Earth years to complete one orbit around the Sun. This means that since Herschel's discovery in 1781, Uranus has completed only about 2.5 complete orbits. In the same period, Earth has completed 245 orbits. The scale of Uranian time is difficult to internalize. An 84-year year means that someone born at the start of a given season on Uranus would die of old age before that season ended. Uranus's orbit is not perfectly circular, but is more circular than most of the outer planets' orbits. Its eccentricity is only about 0.046, small enough that the variation in solar energy received between perihelion and aphelion is modest compared to what Mercury or even Mars experiences. The distance from the Sun changes by less than 15% between closest and farthest approach over the course of an orbit. At Uranus's distance, the solar wind is attenuated. The stream of charged particles flowing outward from the Sun is less intense and slower than at Mercury or Earth. The interplanetary environment near Uranus is quieter, less driven by solar activity, shaped more by Uranus's own magnetic field and radiation environment than by direct solar influence. This makes Uranus's magnetosphere somewhat different in character from the magnetospheres of the inner planets, though as we'll see, Uranus's magnetic field itself is unusual enough to make the magnetosphere genuinely strange. Before moving on to the most distinctive feature of Uranus, its tilt, let's note one more property of its orbit: the relationship between its year and its seasons. On Earth, axial tilt of 23.5 degrees produces seasons, but these seasons repeat on a yearly cycle, which lasts only 365 days. On Uranus, the 84-year orbital period means that each of Uranus's seasons lasts about 21 Earth years. 21 years of summer, 21 years of autumn, 21 years of winter, 21 years of spring. In the course of a single human lifetime, you would experience Uranus's complete seasonal cycle at most once, and likely not even that. The defining characteristic of Uranus, the fact that distinguishes it from every other planet in the solar system and that shapes everything about its environment, its seasons, its magnetosphere, and its history, is its axial tilt. Uranus rotates on its side. More precisely, its rotation axis is tilted approximately 97.8 degrees from the vertical perpendicular to its orbital plane. For reference, Earth's axis is tilted about 23.5 degrees from vertical. Mars is tilted about 25 degrees. Saturn about 27. Venus is tilted about 177 degrees, nearly inverted, which is equivalent to saying it rotates with essentially zero tilt, but in the retrograde direction. Uranus, at nearly 98 degrees, is in an almost unique position. It is tilted far enough that it rolls through its orbit somewhat like a ball rolling along the ground. with its poles alternately pointing roughly toward and away from the Sun as it proceeds around its 84-year orbit. A person watching Uranus from above its north pole during a solstice would see something almost unreal. The Sun would not rise and set in the ordinary way. It would circle slowly, staying above the horizon for years, while the opposite pole received no direct sunlight at all. The rings and moons, because they share the planet's tipped equatorial plane, would appear to move around the planet like a tilted clock face laid across space. The moons follow the planet's tilt because they likely formed in a disk around Uranus, or were reorganized into that plane after the event that tipped the planet. That means the entire inner system is sideways. The rings are sideways. The regular moons are sideways. The magnetic field is not simply sideways with them. It is tilted again in a different direction, creating a system where nearly every important axis points somewhere unexpected. This makes Uranus visually elegant in diagrams, but physically difficult. Most planetary systems have a kind of alignment: orbital plane, equator, rings, moons, magnetic field, and solar wind interact in geometries that are at least partly intuitive. Uranus breaks that intuition. It is not enough to imagine a tilted planet. You have to imagine a tilted planet whose magnetic field is also misaligned, whose seasons last decades, whose moon system shares the tilt, and whose atmosphere may respond slowly to heating patterns that change over human generations rather than days or months. This is one reason Uranus is hard to explain quickly and easy to underestimate. Its strangeness is geometrical before it is visual. You cannot see most of the weirdness at a glance. You have to understand the angles. The consequence of this extreme tilt for Uranus's seasons is unlike anything on any other planet. During Uranus's summer in the northern hemisphere, the North Pole points roughly toward the Sun. For 21 years, the North Pole receives continuous sunlight, a sun that never sets, tracing small circles in the sky but never dipping below the horizon, while the South Pole is in continuous darkness, a 21-year winter night. Then, as Uranus moves around its orbit, the Sun's angle relative to the poles changes. First, the equatorial regions come into sunlight, and the poles receive more moderate illumination. Then the South Pole begins to turn toward the Sun, and for the next 21 years the South Pole receives continuous daylight, while the North Pole endures continuous darkness. At equinox, which occurs roughly every 42 years, twice per Uranian orbit, the Sun illuminates both hemispheres equally, rising and setting near the equator, with normal day-night cycles across the planet. These equinoxes are the only times in Uranus's orbit when anything resembling normal planetary seasons occurs. The rest of the time, Uranus is in a configuration that has no real analog elsewhere in the solar system. One pole baking in continuous summer sunlight for decades, while the other sits in continuous winter darkness. Voyager 2 arrived at Uranus in January 1986, close to the time of Uranus's southern hemisphere summer solstice, the point in its orbit when the South Pole was aimed most directly toward the Sun. This meant that from Voyager 2's perspective as it approached, Uranus appeared as a nearly circular disk with the South Pole prominently visible, the rings appearing nearly as circles around the pole rather than as ellipses across the planet's face, and the moons orbiting in what appeared to be nearly face-on circles rather than back-and-forth arcs. The entire Uranian system, viewed from the approaching spacecraft, looked like a target with the rings as rings and the moons as concentric circles, a configuration peculiar to the geometry of Uranus's tilt and Voyager's approach direction. The seasons of Uranus are not just long versions of Earth's seasons. They are structurally different. On Earth, even in the Arctic and Antarctic, the poles experience long days and nights, but the rest of the planet keeps a familiar rhythm. Most places still have ordinary daily cycles. On Uranus, The geometry of sunlight is so extreme that the entire pattern of atmospheric heating is reorganized. The poles matter in a way they do not on most planets. For a planet with an atmosphere, this is not a small detail. Sunlight determines where gases warm, where they cool, where air rises, where it sinks, and where clouds form. But Uranus rotates quickly, once every 17 hours, while receiving sunlight in a pattern controlled by an 84-year orbit and a 98-degree tilt. The atmosphere is therefore being asked to respond to two clocks at once, a fast rotational clock and a very slow seasonal clock. Those clocks do not produce simple weather. At solstice, one pole receives continuous sunlight for decades, while the opposite pole remains in darkness. You might expect the sunlit pole to become dramatically warmer. Yet observations suggest that Uranus does not behave in a simple way. The atmosphere transports heat, clouds form at different levels, methane condenses and absorbs light, and internal heat, weak though it is, still contributes something. The result is a climate system that cannot be understood by analogy alone. It must be measured. This is one of the reasons Uranus is so valuable scientifically. It is a natural experiment in extreme obliquity. If you want to know what happens to a giant planet when its axis is nearly horizontal, Uranus is the only nearby example. Exoplanet systems almost certainly contain tilted worlds. Giant impacts and gravitational interactions are common in young systems. A planet with a Uranus-like tilt around another star might have extreme polar seasons, unusual cloud cycles, and atmospheric patterns that differ sharply from planets with more ordinary axial tilts. Uranus lets us study that physics close enough to matter. The 2007 equinox was especially important because it was the first Uranian equinox that modern instruments could observe in detail. Voyager 2 saw Uranus near solstice. Hubble, Keck, and other observatories watched it as the equator turned toward the sun. That change in viewing geometry and illumination revealed more atmospheric activity than Voyager had shown. Storms and cloud features appeared. The planet was not dead. It had simply been caught by Voyager at one moment, in one season, at one wavelength, under one geometry. That is the danger of studying a planet only once. A flyby can make a planet seem simpler than it is. It freezes a dynamic world into one historical image. For Uranus, that image was a smooth blue-green sphere, and that image shaped public perception for decades. But the planet was never only that image. It was a seasonal world caught at a quiet-looking moment. The formation of Uranus is also linked to the larger question of planetary migration. The giant planets probably did not form exactly where they are now. Interactions with the disk of leftover planetesimals and with one another likely shifted their orbits during the early history of the solar system. Uranus and Neptune may have formed closer to the Sun and then moved outward, scattering icy bodies and helping shape the Kuiper Belt. If Uranus was tilted by a giant impact during this chaotic era, then its current state preserves evidence of both formation and disruption. Its sideways spin may be the frozen result of one violent event. Its moons may have formed, reformed, or been reorganized after that event. Its interior layering may have been influenced by impact energy. Its faint rings may be connected to later collisions in a system already altered by the original catastrophe. That means Uranus is not only a planet. It is a historical record of the early outer solar system, written in geometry and internal structure rather than in obvious surface rocks. The question of what caused Uranus's tilt is one that planetary scientists have debated since it was first recognized, and the answer is not fully settled even today. The most widely accepted hypothesis is that Uranus was struck by a large object, a protoplanet possibly as large as the Earth itself, or perhaps several Earth masses, during the early solar system, when giant impacts between large objects were far more common than they are today. This impactor struck Uranus at roughly the right angle to tip its rotation axis to its current orientation. The impact would have been enormously energetic, depositing significant heat into Uranus's interior. This immediately raises a problem that we'll return to in detail. Uranus currently radiates essentially no excess internal heat. Unlike Jupiter, Saturn, and Neptune, all of which radiate significantly more energy than they receive from the Sun, evidence of residual internal heat from formation. Uranus radiates only approximately as much energy as it receives. If a massive impact deposited enormous heat into Uranus's interior, where did that heat go? Why does Uranus appear so thermally quiescent compared to the other giant planets? One possibility is that the impact occurred under specific conditions that allowed the heat to be concentrated in one region of the interior. Perhaps the impact heated the outer layers while leaving the deeper interior relatively cool, creating a temperature stratification that inhibits convection and prevents the interior heat from migrating to the surface and being radiated away. Another possibility is that Uranus was not struck by a single large impactor, but by multiple smaller objects, each insufficient to dramatically heat the interior. A third possibility is that compositional differences from Neptune, perhaps in the distribution of icy materials in the mantle, create a thermally insulating layer that traps heat below. The honest answer is that the mechanism responsible for Uranus's thermal inertness remains genuinely uncertain, and it's one of the primary scientific questions that motivates future exploration of the planet. An alternative to the giant impact hypothesis for the tilt involves more complex gravitational dynamics during the early solar system. Scenarios in which the mutual gravitational interactions of the giant planets during a period of orbital instability drove Uranus's tilt to its current value through accumulated orbital perturbations rather than through a single catastrophic collision. These models tend to predict different outcomes for the interior structure and heat budget, and can in principle be tested against observations. But the observational constraints on Uranus's interior are currently too limited to definitively discriminate between scenarios. What is not in question is the consequences of the tilt. The seasonal extremes on Uranus are among the most dramatic in the solar system, and they drive unusual atmospheric dynamics. The 21-year polar winters and summers create conditions where one hemisphere is cut off from solar heating for decades at a time, creating temperature gradients that should, in principle, drive powerful atmospheric circulation. And yet, when Voyager 2 arrived, Uranus appeared almost featureless, calm, bland, lacking the obvious storm systems and banding patterns visible on Jupiter, Saturn, and Neptune. This apparent atmospheric quiescence was one of the more puzzling aspects of the 1986 flyby, and subsequent observations have suggested that Uranus's atmosphere is more dynamic than Voyager 2's limited encounter suggested, with storms and cloud features appearing in the intervening decades. Before diving into what Uranus is made of and what happens inside it, let's settle the most basic question. What are we looking at when we observe Uranus? Uranus has a diameter of about 51,100 kilometers, roughly 4 times Earth's diameter, and very slightly larger than Neptune's diameter. Its mass is about 14.5 times Earth's mass, making it slightly less massive than Neptune despite being slightly larger. This means Uranus is less dense than Neptune, about 1.27 grams per cubic centimeter, compared to Neptune's 1.64, which reflects meaningful differences in their internal compositions and structures. In terms of appearance, Uranus is a pale, blue-green world. The color comes from methane in its upper atmosphere, which absorbs red wavelengths of sunlight and reflects blue-green wavelengths back to the observer. At visible wavelengths, Uranus appears as a smooth, nearly featureless disk, no obvious banding like Jupiter and Saturn, no dramatic dark spots, no visible storm systems during the Voyager 2 flyby. This apparent blandness was striking in 1986 and remained puzzling for years, and will return to why it's misleading. Uranus rotates once on its axis in approximately 17 hours and 14 minutes. However, this rotation period is complicated by the same differential rotation that affects all gas and ice giants. Different latitudes rotate at slightly different speeds, and the planet has no solid surface from which to measure a definitive rotation period. The 17-hour period represents the rotation of the interior, measured through the rotation of the magnetic field, which is considered the most reliable proxy for the interior's rotation rate. The planet's mass and size combine to produce a surface gravity of about 8.7 meters per second squared, about 89% of Earth's surface gravity, very similar to Saturn's. A person standing on Uranus's cloud tops would weigh slightly less than on Earth, an unremarkable figure for such a physically extreme planet. Uranus has an escape velocity of about 21.3 kilometers per second, roughly twice Earth's. This is high enough that Uranus has no difficulty retaining its hydrogen and helium atmosphere, even at the elevated temperatures that occur in the outer layers of the atmosphere. There is a useful way to think about Uranus's coldness. Cold does not mean still. On Earth, cold air can move violently. On Uranus, the atmosphere can be extremely cold at the top and still support fast winds, complex circulation, and seasonal cloud activity. Temperature alone does not define activity. What matters is how energy moves, how gases condense, how rotation organizes flow, and how the atmosphere responds to slow changes in sunlight. This is one of the reasons the phrase coldest atmosphere should not make Uranus sound dead. The upper atmosphere reaches extremely low temperatures, but beneath that level the planet contains deeper layers of gas and fluid where pressure and temperature rise. The visible cloud tops are only the outer skin of a much deeper system. A cold skin can cover a complicated interior. The same is true for the planet's appearance. Uranus may be pale and smooth in ordinary images, but that surface smoothness is partly the result of methane haze hiding contrast. A storm on Uranus does not always present itself like a bright red oval on Jupiter. It may be easier to detect in infrared. It may appear briefly, drift, fade, or change with season. Some clouds may be high, others deep. Some may be tied to polar chemistry, others to rising methane or hydrogen sulfide. The visible disk gives only a partial answer. For the channel, this is what makes Uranus a strong topic. The viewer's first impression is wrong. The planet looks like the least dramatic outer world, but every layer beneath that impression introduces a contradiction. Quiet image, extreme tilt. Smooth disk, violent geometry. Cold atmosphere, complicated winds. Small-looking moons, enormous cliffs. Dark rings, delicate dynamics. One flyby, decades of unanswered questions. That kind of reversal is good science and good storytelling. The apparent blandness of Uranus is also a lesson in how planetary images can mislead. Human eyes are tuned to visible light, but giant planets often reveal their most important structures outside the visible range. Methane absorbs strongly in certain infrared wavelengths, so infrared observations can isolate high-altitude clouds, deeper cloud decks, and polar structures that visible images flatten into a nearly uniform disk. A planet can look empty in one wavelength and active in another. This is not a failure of the image. It is a reminder that planets are layered. The visible surface of Uranus is not a surface at all, but a level in the atmosphere where light happens to scatter back to space. Above that level are hazes and high clouds. Below it are deeper cloud layers and winds. Still deeper, the atmosphere becomes warmer, denser, and less familiar. No single photograph can capture that vertical structure. Clouds on Uranus are not just decorative features. They are markers of temperature, altitude, composition, and motion. A bright cloud can mean methane ice has condensed in rising air. A dark band can indicate a different level of absorption. A polar cap can reveal seasonal changes in haze or methane distribution. A storm that appears suddenly tells us that the atmosphere has crossed some threshold of instability. Each feature is a clue to processes that are mostly invisible. The planet's weak internal heat makes these clues more difficult to interpret. On Jupiter and Saturn, strong heat from the interior helps drive convection and visible banding. Neptune, despite being farther from the Sun, has enough internal heat to produce dramatic storms and extremely fast winds. Uranus has less obvious internal energy reaching the atmosphere, so solar heating and seasonal forcing may play a larger relative role. But because Uranus's solar forcing is distorted by its extreme tilt, the atmosphere becomes a puzzle of competing influences. A future atmospheric probe would change this. It could measure temperature, pressure, wind, methane, ammonia, hydrogen sulfide, noble gases, and isotopic ratios as it descended. Those measurements would tell us not just what Uranus's visible atmosphere contains, but what the planet as a whole inherited during formation. Noble gases are especially important because they are chemically inert. They do not easily react away or become trapped in surface rocks. Their abundances act like fingerprints of the environment in which the planet formed and the icy planetesimals it accreted. In that sense, an atmospheric probe is not simply a weather station. It is a time machine into the formation of the outer solar system. Uranus's atmosphere is where its appearance resides, and it is both simpler and more interesting than its bland, visible wavelength appearance suggests. The outermost layers of Uranus's atmosphere are composed primarily of hydrogen, about 83%, with helium making up about 15% and methane providing the remaining 2 to 3%. These proportions are broadly similar to Neptune's, and the presence of methane at a few percent is what gives both planets their distinctive blue-green color by absorbing red light from sunlight and reflecting the blue-green remainder. But Uranus appears significantly bluer than Jupiter and Saturn, and distinctly less blue than Neptune, sitting somewhere between the two. The precise color depends on the altitude and thickness of the methane cloud layers and on additional absorbers in the atmosphere. One of the long-standing mysteries about Uranus's color, noted since the Voyager flyby, is that it appears slightly different from Neptune despite both planets having broadly similar methane concentrations. Something else, an additional absorber not yet fully identified, may be contributing to Neptune's deeper blue color, or there may be differences in the vertical distribution of methane and haze particles between the two planets that affect the color even though the bulk compositions are similar. The atmosphere is divided into layers. At the top, above the main cloud deck, is a clear, cold region where temperatures fall to around -224 degrees Celsius, the coldest temperature of any planetary atmosphere in the solar system. Cold enough that Uranus holds the record for lowest atmospheric temperature in the solar system, beating even Neptune despite Neptune being farther from the Sun. This extreme cold at the top of the atmosphere is partly a consequence of Uranus's lack of internal heat. Without internal heat rising from below, the upper atmosphere cools to very low temperatures, lower than would be expected purely from solar heating at this distance. Below the cold, clear upper atmosphere, the main visible cloud deck is a layer of methane ice clouds. Methane condenses at the temperatures found in this region, forming ice crystals that scatter light and produce the reflective, bright appearance of the cloud tops when viewed at certain wavelengths. At longer, near-infrared wavelengths that penetrate the methane clouds, ground-based observers using adaptive optics have detected underlying cloud features, patterns of brighter and darker cloud structures at different altitudes, that reveal an atmosphere more dynamically active than the bland visible wavelength appearance suggests. Below the methane cloud layer, temperatures and pressures increase with depth, and different chemical species condense at different levels, producing distinct cloud layers of ammonia ice, then ammonium hydrosulfide, and eventually, at sufficient depth, water ice. The atmosphere transitions gradually from gas to a state that is neither quite gas nor liquid as pressure increases, eventually blending into the icy mantle of the planet's interior. The winds in Uranus's atmosphere are strong. Wind speeds of several hundred kilometers per hour have been measured in the cloud-top region. As with Neptune, the equatorial winds blow in the retrograde direction, opposite to the planet's rotation, while mid-latitude winds blow in the prograde direction. This retrograde equatorial circulation, shared with Neptune and not seen on Jupiter or Saturn, is a feature of ice giant atmospheres that current models attribute to the different interior heat distribution and atmospheric structure of ice giants compared to gas giants. But the detailed mechanisms are still being worked out. One of the most dramatic changes in Uranus's atmospheric appearance occurred after the planet passed its equinox in 2007. As the sun moved from illuminating the South Pole to illuminating the equatorial regions, and then the North Pole, Uranus's atmosphere began showing significantly more cloud activity than had been observed in the preceding decades. Large storms, complex banding patterns, and bright cloud features began appearing in observations from the Hubble Space Telescope and from ground-based observatories using adaptive optics. In 2014, a particularly large and complex storm system appeared in Uranus's northern hemisphere, bright enough that amateur astronomers could detect it in modest backyard telescopes, a storm comparable in visible extent to the Great Red Spot on Jupiter. This emergence of atmospheric activity after the equinox suggests that Uranus's atmosphere does respond to seasonal changes, that the 21-year shift in solar heating from one hemisphere to another does drive changes in atmospheric dynamics over time. The transition from solstice, when one pole receives maximum heating, to equinox, when both hemispheres receive comparable heating, appears to trigger increased atmospheric instability and storm formation. This has implications for how scientists model Uranus's atmosphere and for what we might expect to see in future observations as Uranus approaches its northern solstice in 2028. The interior of Uranus, what lies beneath the visible atmosphere, is where the planet's most unusual properties originate and where our knowledge is most limited. The word ice can make Uranus sound colder and simpler than it is. Deep inside the planet, water, ammonia, and methane are not frozen blocks. They are compressed into hot, dense, electrically conducting fluids. At sufficient pressure, molecules break apart, ions move freely, and materials take on properties that do not exist at the surface of Earth. The interior of Uranus is not a frozen ocean. It is a deep chemical engine operating under pressures that would crush ordinary matter into unfamiliar states. Some models suggest that the interior may not be well mixed. Instead of a simple structure, core, mantle, atmosphere, Uranus may have gradual layers where composition changes with depth. Heavier material may be more concentrated below, lighter material above, with boundaries that slow convection. If so, the planet could be internally hot while appearing cold from outside. Heat trapped beneath stable layers would not easily reach the cloud tops. This makes Uranus a possible example of a planet with a hidden heat reservoir. The planet may not be cold all the way down. It may be cold only where we can see it. That distinction is important. A world can appear inactive not because it lacks energy, but because the energy cannot escape efficiently. The same layered structure could influence the magnetic field. If the conducting region is not a deep central core, but a shell or layer within the mantle, the resulting dynamo would naturally be more asymmetric. It would not produce a clean dipole like Earth's. It would produce something tilted, offset, and complicated, exactly the kind of magnetic field Voyager measured. This is why Uranus's low heat and strange magnetism may not be separate mysteries. They may be different symptoms of the same interior structure. Diamond rain belongs to this same category of deep interior physics. It is an attention-grabbing phrase, but the underlying idea is serious. Carbon separated from methane under pressure may crystallize and sink. If that happens, it changes how energy and material move inside the planet. It may contribute to heat transport. It may alter the distribution of carbon. It may be part of a wider set of exotic high-pressure processes common inside ice giants. We do not yet know how much of this is happening in Uranus, but the possibilities themselves show why the planet matters. Uranus is not simply a colder Neptune or a smaller gas giant. It is a laboratory for forms of matter that we can only briefly create in experiments and only indirectly infer in planets. Uranus is classified as an ice giant, a category shared only with Neptune among the solar system's planets. The term ice giant is somewhat misleading, as we discussed briefly with Neptune. The ice refers to the high-pressure fluid state of materials that are icy under ordinary conditions: water, ammonia, and methane. In Uranus's mantle, these materials exist at temperatures of thousands of degrees Celsius and pressures of millions of atmospheres, conditions under which they are anything but the ordinary ices of everyday experience. The interior of Uranus is thought to consist of three broad zones. The outermost is the atmosphere we've already discussed: hydrogen, helium, and methane in gaseous and then increasingly compressed form, blending gradually into the mantle below. The mantle, which constitutes the bulk of the planet's mass and volume, is composed primarily of water, ammonia, and methane in their high-pressure fluid forms, mixed with dissolved rocky and metallic materials. Deep within the planet, there may be a rocky or metallic core of heavier elements, silicates and metals, though the size and composition of this core are poorly constrained. The pressures and temperatures within Uranus's mantle are sufficient for some of the same exotic phenomena that have been predicted for Neptune's interior. In particular, diamond rain, the crystallization of carbon from methane molecules under extreme pressure, producing diamond particles that sink toward the core, may be occurring in Uranus's mantle, just as it may be occurring in Neptune's. Laboratory experiments using high-power lasers to reproduce the relevant pressure and temperature conditions have produced results consistent with diamond formation under mantle-like conditions. The carbon rain hypothesis is not confirmed, but it is consistent with the best available models and the available experimental evidence. A crucial and still poorly understood property of Uranus's interior is its relationship with heat. As mentioned, Uranus radiates essentially no excess internal heat. It appears to be in nearly perfect radiative balance with the sunlight it receives, emitting only about 14% more energy than it absorbs. Compare this to Jupiter, which emits nearly twice what it receives, Saturn, which emits about 78% more, and Neptune, which emits about 160% more. Uranus is dramatically, anomalously cold relative to the other giant planets. The hypothesis that a compositional gradient, a region within Uranus's mantle where heavier materials are more concentrated than lighter ones, might inhibit convection and trap internal heat below the surface, is one of the leading explanations. If the mantle is thermally stratified, not because of temperature but because of composition, then the convective mixing that normally carries heat from the hot, deep interior to the cooler outer layers would be suppressed. Heat would accumulate in the deep interior rather than reaching the surface, and the planet's outer layers would appear cold even though the interior is hot. This layered structure hypothesis has some support from models, but testing it directly requires knowledge of Uranus's interior density profile that current observations cannot provide with sufficient precision. Gravity measurements from an orbiting spacecraft, combined with seismology-like measurements of Uranus's oscillation modes, if they can be detected, could potentially constrain the interior structure well enough to determine whether compositional layering is responsible for the heat deficit. The heat mystery is scientifically significant because it affects almost every other aspect of Uranus's physics. Interior heat drives atmospheric dynamics. It influences the dynamo generating the magnetic field. It determines the rate of cooling and contraction over the planet's history. Understanding why Uranus retains its heat while Neptune, of similar size and composition, releases it freely is understanding something fundamental about how these planets formed and evolved. The comparison with Neptune makes the mystery sharper. Neptune is farther from the Sun, yet it has a more active-looking atmosphere and emits far more internal heat relative to the sunlight it absorbs. Uranus is closer, but colder in its upper atmosphere and less luminous from within. Two planets often grouped together as twins behave as if their interiors were built or damaged in very different ways. This may be a clue to Uranus's past impact. If a giant collision knocked Uranus onto its side, it might also have altered the way heat moves through the planet. It may have created layers that resist convection, trapping warm material beneath cooler material instead of allowing the whole interior to mix. In a giant planet, convection is not a decorative detail. It is the way the planet releases memory. Heat left over from formation, heat released by separation of materials, heat stored in deep layers. All of it can reach the atmosphere only if the interior can move it upward. If the interior is layered, Uranus may be holding a record of its early violence deep below the visible clouds. This possibility makes Uranus more interesting, not less. A planet that looks quiet at the surface may be quiet because its interior is locked. Its calmness could be a symptom of hidden structure. A magnetosphere like Uranus's would be difficult enough to understand even if the planet were upright. With the planet tilted on its side, the system becomes far stranger. The rotation axis, magnetic axis, and direction of the solar wind are all badly misaligned. As Uranus turns, the magnetic field sweeps through space in a corkscrew-like motion, twisting the magnetotail behind the planet. Charged particles trapped in the field do not move through a simple, symmetric environment. They move through a magnetic structure that changes orientation dramatically every rotation. This matters for the moons. The major moons orbit in the planet's equatorial plane, which is also tipped with the planet. As Uranus rotates, its magnetosphere can expose different surfaces of the moons to different charged particle environments. Radiation can darken ice, alter organic compounds, create new surface chemistry, and modify the reflectivity of the leading and trailing hemispheres. When we look at color differences on Uranus's moons, we may be seeing not only geology, but the long-term imprint of this bizarre magnetic environment. It also matters for auroras. On Earth, auroras occur near the magnetic poles, which are relatively close to the geographic poles. On Uranus, magnetic poles are far from the rotation poles and displaced from the center. Auroral emissions can therefore appear in unexpected places and shift in ways that are difficult to predict without detailed magnetic mapping. Observing Uranian auroras from Earth and with space telescopes gives clues, but only an orbiter could follow the system continuously enough to understand how solar wind energy enters and moves through it. Magnetospheres are sometimes treated as invisible technical details, but they are part of a planet's environment. They shape plasma, radiation, atmospheric escape, surface chemistry on moons, and the interaction between a planet and the Sun. Uranus's magnetosphere is not a minor curiosity. It is one of the most unusual natural plasma laboratories in the solar system. Uranus's magnetic field is as unusual as anything about the planet, and its strangeness is of a different kind from Jupiter's or Saturn's strong, relatively simple fields. Earth's magnetic field is generated by convection in the liquid iron outer core, producing a largely dipolar field, two poles, one roughly north and one roughly south, with the field orientation within about 11 degrees of the planet's rotation axis. Most gas giant planets have similarly organized dipolar fields. Jupiter's is tilted about 10 degrees from the rotation axis. Saturn's is almost perfectly aligned. These are the kinds of magnetic fields that straightforward dynamo theory predicts. Uranus's magnetic field is tilted about 60 degrees from its rotation axis. And it is not only tilted, it is also offset, with the center of the magnetic dipole displaced about 8,000 kilometers from the geometric center of the planet, roughly a third of the planet's radius. The result is a magnetic field that is dramatically different from any other in the solar system. On one side of the planet, the magnetic poles are much closer to the surface. On the opposite side, they are much farther away. The field strength varies enormously across the planet's surface. As Uranus rotates, its tilted and offset magnetic field does not simply rotate uniformly. It wobbles. The planet's magnetic poles trace large circles around the rotation axis rather than sitting fixed near it. The magnetosphere, the region of space dominated by Uranus's magnetic field, is therefore not a stable, symmetric structure like Earth's or Jupiter's magnetosphere, but a wobbling, asymmetric, constantly shifting structure that presents very different faces to the solar wind as Uranus rotates. Neptune shares this peculiarity of having a highly tilted and offset magnetic field, which is one of the lines of evidence suggesting that both ice giants share a similar interior structure, specifically, that both have their magnetic dynamos operating in the high-pressure water-ammonia mantle rather than in the deep core, as is the case for Earth and probably for Jupiter and Saturn. A mantle dynamo, operating in a conducting fluid at large radius, but not at the very center of the planet, would naturally produce a more complex, more asymmetric field than a core dynamo. Because the geometry is less symmetric, and because convective flows in the mantle can be more complex and less organized than flows deep in a core. The detailed structure of Uranus's magnetic field shows not just a dipole, but significant contributions from higher-order multipole terms, quadrupole, octupole, and higher, which indicate that the field-generating region is distributed through a significant volume of the interior rather than concentrated in a small, deep core. The 1986 Voyager 2 measurements characterized the field well enough to establish the basic parameters, but they could not follow the magnetosphere through Uranus's full range of rotations, solar wind conditions, and seasons. A Uranus orbiter with modern fields and particles instruments could finally map this system as a changing environment rather than as one frozen flyby snapshot. One of the more dramatic consequences of Uranus's tilted, offset, rotating magnetic field is the nature of its interaction with the solar wind. On Earth, Jupiter, and Saturn, the magnetosphere has a relatively stable, consistent shape. The solar wind flows around it. The magnetopause is at a relatively constant distance from the planet, and the structure doesn't change dramatically during a rotation. On Uranus, because the magnetic axis is so far from the rotation axis, the magnetosphere literally changes its overall shape during each rotation. The magnetic field flips from being nearly aligned with the solar wind to nearly perpendicular to it and back again every 17 hours. The result is a magnetosphere that reconnects with the solar wind magnetic field in complex, oscillating patterns that are unlike anything seen at any other planet. Understanding this unusual magnetosphere more completely requires extended observations from an orbiting spacecraft, not the brief snapshot that Voyager 2 could provide during its flyby. This is one of the specific scientific objectives of the Uranus Orbiter and Probe mission that has been identified as the top priority for the next decade of planetary science. The modern view of Uranus has also changed because of the James Webb Space Telescope. In visible light, Uranus can look almost blank, a smooth blue-green ball with little obvious detail. In infrared light, Webb showed a much more active world. Its images revealed the planet's rings with unusual clarity, including faint inner and outer rings that are difficult to see in ordinary images, and showed the bright north polar cap and cloud structures that become more apparent as Uranus approaches its northern summer solstice. This matters because Uranus is a seasonal planet in an extreme way. Its north pole has been turning more directly toward the sun since the 2007 equinox, and the northern polar region has become easier to study from Earth and from space telescopes. Webb's infrared view does not replace a spacecraft mission, but it helps reveal how much the visible image conceals. The pale, quiet planet of the Voyager pictures is not the whole Uranus. It is only one wavelength, one season, one brief geometry. Webb observations have also sharpened the picture of the Uranian moon system. Small moons near the rings are difficult to see because they are faint, dark, and lost in glare from the planet and rings. Recent deep observations have added to the known count and suggest that the Uranian system may still contain small, undiscovered moons. This is not just a matter of naming more objects. Tiny moons can act as shepherds, sources of ring dust, markers of past collisions, and clues to the dynamical history of the entire system. So when we say Uranus has rings and moons, we are not describing a static arrangement. We are describing a system that is still being resolved piece by piece, with each new observation changing the map slightly. Uranus has rings. Most people don't know this, which is understandable. Uranus's rings are nothing like Saturn's magnificent ring system. They are narrow, dark, and barely visible even with professional instruments. But they were discovered under remarkable circumstances, and they reveal something important about the Uranian system. The discovery came on March 10, 1977. A team of astronomers, including James Elliott, Edward Dunham, and Douglas Mink, were observing Uranus from the Kuiper Airborne Observatory, a specially equipped aircraft carrying a telescope above most of Earth's atmosphere. Their goal was to study Uranus's atmosphere by observing the light from a star as Uranus passed in front of it, a stellar occultation. As Uranus moved in front of the starlight would be gradually dimmed and refracted by Uranus's atmosphere in ways that would reveal the atmospheric structure. What they observed was more than they expected. Well, before Uranus itself blocked the star's light briefly dimmed, then brightened again, then dimmed and brightened several more times. Then Uranus occulted the star completely. And then, on the other side of the planet, after the star emerged, the same pattern of brief dimmings and brightenings occurred in mirror image. The symmetrical pattern before and after the occultation could only mean one thing. Something in orbit around Uranus, rings, was blocking the star's light before and after the planet itself did. This was the first discovery of a ring system other than Saturn's, and it was discovered not by imaging the rings directly, but by observing their effect on starlight, by inference rather than direct observation. The Voyager 2 flyby in 1986 confirmed the rings directly through both direct imaging and through additional stellar occultation observations with the spacecraft's instruments. The discovery method of the rings also gives them a certain scientific elegance. No one saw beautiful arcs or bands in a photograph. Instead, the rings betrayed themselves by removing light. A star blinked, not once, but several times, before Uranus passed in front of it. Then it blinked again in reverse order after Uranus moved away. The symmetry was the evidence. Something invisible had written its presence into the light curve. That is a powerful kind of discovery because it shows how astronomy often works. We do not always see objects directly. We see what they do. We see a star dim, a planet wobble, a spectrum shift, a signal disappear for a fraction of a second. From that absence, we infer structure. Uranus's rings were found in the same spirit as many exoplanets, not by looking at a world clearly, but by measuring the light it interrupts. The rings themselves are probably not permanent in the deepest sense. Dark narrow rings require confinement. Dusty outer rings require sources. Small moons collide with micrometeorites and shed particles. Shepherd moons sculpt edges. Resonances create patterns. Over millions of years, material can spread, fall inward, collide, or gather into moonlets. The ring system we see today may be one phase in a long cycle of disruption and reassembly. This makes the Uranian rings less visually grand than Saturn's, but not less scientifically meaningful. Saturn's rings overwhelm the eye. Uranus's rings challenge the mind. They are dark, thin, difficult, and dynamic. A ring system that exists at the edge of visibility and forces observers to extract structure from faint signals. Uranus has 13 known distinct rings, though the system has evolved as measurements have improved. The rings are named partly with numbers and partly with letters from the Greek alphabet, a naming scheme that reflects the history of gradual discovery. The innermost rings are designated 1986 U2, R, and Zeta. Moving outward come rings 6, 5, 4, Alpha, Beta, Eta, Gamma, Delta, Lambda, Epsilon, Nu, and Mu. The Epsilon ring is by far the most prominent and the best studied. It is about 100 kilometers wide, has a higher reflectivity than the other rings, and shows a measurable variation in width around its circumference. It is wider at some points in its orbit than at others, a variation that reflects the non-circular shape of the ring and its interaction with the shepherd moons that contain it. Two small moons, Cordelia and Ophelia, orbit just inside and just outside the Epsilon ring, and their gravitational influence confines the ring material and prevents it from spreading. These shepherd moons are themselves dark and difficult to observe, discovered during the Voyager 2 flyby and barely detectable since. The other rings of Uranus are narrow. Most are only a few kilometers wide and extremely dark, reflecting only a few % of the light that hits them. This very low albedo, similar to that of charcoal or fresh asphalt, makes the rings nearly invisible against the black of space and accounts for why they were not detected visually before the 1977 occultation. The dark material is thought to be radiation-processed organic compounds, the same general category of material that darkens many objects in the outer solar system. But the precise composition has not been fully characterized. Hubble Space Telescope observations in the 1990s and 2000s found additional diffuse rings, the Nu and Mu rings, beyond the main ring system. These outer rings are fainter, broader, and bluer in color than the inner rings, which suggests they contain smaller particles, fine dust rather than the larger chunks that make up the main rings. The source of this dust is probably the inner small moons, from which micrometeorite impacts continuously knock off particles that spread into these faint diffuse rings. The age and origin of Uranus's rings are not well established. They may be relatively young, perhaps 1 billion years old or less, formed from the disruption of a moon or moons by tidal forces or by collisions within the ring region. Alternatively, some material may be primordial, surviving from the early solar system. The narrow, dark character of the main rings is consistent with them being geologically young. Ring systems tend to spread and fade over time as orbital dynamics disperse the material, and the current state of the rings might represent a relatively recent phase in the ring system's evolution. The 2007 equinox of Uranus provided a unique opportunity to observe the ring's edge-on from Earth, as the ring plane aligned with our line of sight. During this brief period, astronomers using large ground-based telescopes imaged the rings at unfamiliar orientations and detected new details about their structure, including evidence for small embedded moonlets and variations in ring brightness that are still being interpreted. Uranus has more than 24 known moons, all of them named after characters from the works of William Shakespeare and Alexander Pope. The only moon system in the solar system to follow a completely non-mythological naming convention, a tradition established by the Herschel family and continued as new moons were discovered. The 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are the only ones large enough to have been pulled into roughly spherical shapes by their own gravity, and they represent the scientifically interesting portion of the Uranian moon system. Beyond them, Uranus has more than 20 smaller moons, most of them small, irregularly shaped bodies orbiting either close to the planet within and near the ring system or far out in irregular, often retrograde orbits characteristic of captured objects. Titania and Oberon were the first of Uranus's moons to be discovered, found by William Herschel in 1787, just 6 years after the planet itself. Ariel and Umbriel were discovered in 1851 by William Lassell, and Miranda was found in 1948 by Gerard Kuiper. All 5 were observed only distantly from Earth until Voyager 2 arrived in 1986 and provided the first close-up views. The Shakespearean naming convention, while charming, has had practical consequences, as astronomers have continued to discover small, irregular Uranian moons with improved instruments. They have had to mine increasingly obscure corners of Shakespeare's canon for character names. Recent inner small moons are named after characters from The Tempest, Caliban, Prospero, Setebos, Stefano, Trinculo, Sycorax, while some of the irregular outer moons bear the names of Shakespeare characters from plays like A Midsummer Night's Dream, The Merchant of Venice, and even Alexander Pope's The Rape of the Lock. The 5 major moons deserve attention because each is genuinely interesting. Miranda is the smallest and innermost of the 5 major Uranian moons, with a diameter of about 472 kilometers, not much larger than some of the mid-sized asteroids. Despite its small size, Miranda is arguably the most geologically interesting object in the Uranian system, and it was one of the most surprising discoveries of the Voyager 2 flyby. Before the flyby, scientists expected Miranda, given its modest size and presumed old age, to be a relatively bland, heavily cratered world, similar in character to the geologically dead smaller moons of Saturn and other planets. What Voyager 2 found was something completely different and deeply puzzling. Miranda's surface is a patchwork of extraordinarily different terrain types sitting directly adjacent to each other. Parts of the surface are ancient and heavily cratered, similar to what was expected. But adjacent to these ancient regions are enormous, roughly trapezoidal features called coronae, complex regions of grooves, ridges, and cliffs arranged in roughly concentric patterns, looking almost like they were placed on the surface rather than growing organically from geological processes. The coronae are unlike any feature seen on any other moon or planet. They have no obvious analog, and their origin has been debated ever since. The most striking feature on Miranda is Verona Rupes, a towering cliff that descends about 20 kilometers from the edge of one of the coronae to the surface below. 20 kilometers. For comparison, the sheer face of the Grand Canyon in the United States is about 1.5 kilometers high. Everest above sea level is about 8.8 kilometers. Verona Rupes is more than twice Everest's height as a vertical cliff face. It is the tallest known cliff in the solar system. Standing at the top of Verona Rupes and looking down, in Miranda's low surface gravity, about 1/100th of Earth's, would be a different experience from any cliff on Earth. An object falling from the top of the cliff would take about 10 minutes to reach the bottom, falling through Miranda's negligible gravity in a long, slow arc. The view from the top would stretch across a dramatic landscape of ridges, grooves, and ancient craters stretching to a curved horizon only a few kilometers away on this small world. The origin of Miranda's bizarre terrain has generated several competing hypotheses. The early favorite was the catastrophic disruption and reassembly scenario. Miranda was struck by a large impactor and shattered completely, with the fragments reassembling into a jumbled, mixed-up world where material from the interior ended up adjacent to surface material, explaining the patchwork of different terrain types. This scenario has largely fallen out of favor because the physics of reassembly makes it difficult to produce the specific patterns observed without very specific conditions. The current leading hypothesis involves internal convection driven by tidal heating. Miranda's relatively tight orbit around Uranus, combined with resonant interactions with other Uranian moons, may have subjected it to significant tidal heating at certain periods in its history, the same process that drives Io's volcanism and maintains Enceladus's ocean. This tidal heating could have driven convective overturn in Miranda's interior, bringing warm, buoyant material upward through the crust in specific regions, creating the coronae as the expression of these upwelling plumes. The cliffs and ridges associated with the coronae would be the result of the surface responding to the upward push of material from below. This hypothesis remains somewhat speculative because we have only a partial view of Miranda's surface. Voyager 2's flyby geometry meant that only about 45% of the surface was imaged well, with the rest in shadow or at unfavorable viewing geometry. The unimaged hemisphere might contain entirely different terrain, or it might show more coronae, or it might show the ancient, undisturbed craters that were expected to cover the whole moon. We don't know. What we can say is that Miranda is, given its modest size, one of the most geologically complex and surprising small bodies in the solar system. If it has experienced tidal heating significant enough to drive the convection implied by the coronae hypothesis, it may even have had a subsurface ocean in its past, water melted by the tidal heat, subsequently refrozen as the heating subsided. The complexity of its terrain is disproportionate to its size and makes it a priority target for any future mission to the Uranian system. Ariel is the fourth largest Uranian moon and the second from Miranda in outward order, with a diameter of about 1,158 kilometers, more than twice Miranda's. Like Miranda, it shows evidence of past geological activity that distinguishes it from the simpler, more heavily cratered appearance expected of an ancient, geologically dead world. Ariel's surface shows canyons and valleys, suggesting a history of rifting, the crust being pulled apart by extensional forces, similar in principle to the rift valleys found on Earth and on other geologically active solar system bodies. These rifts, some of which are filled with relatively smooth material suggesting later flooding by lava or slush flows, indicate that Ariel experienced geological activity after the period of heavy bombardment that shaped its oldest terrain. Some of the canyon floors show fresh-looking, smooth material that may have erupted from the interior. Either water ice cryovolcanism, where liquid water welled up through cracks and froze on the surface, or flows of more solid material deformed by heat and pressure. Ariel also has the least heavily cratered surface of the 5 major Uranian moons, which is interpreted as indicating that more of its surface has been geologically resurfaced in the relatively recent past, erasing older impact craters. Whether this resurfacing was driven by tidal heating, by residual heat from early formation and differentiation, or by some other process is not certain. The relative youth of Ariel's surface compared to its siblings makes it particularly interesting as a potential target for detailed investigation. Umbriel is in many ways Ariel's opposite. Where Ariel has a relatively young, geologically varied surface, Umbriel has the oldest, most heavily cratered surface of any of the 5 major Uranian moons. It is uniformly dark, darker than the other moons, with a surface albedo of only about 26%, lower than its siblings. Its surface appears ancient and undisturbed, having accumulated craters over the entirety of the solar system's history without significant geological resurfacing. There is one distinctive anomaly on Umbriel's surface, a bright ring visible on the floor of a large crater near the North Pole, named Wunda. The ring is anomalously bright against the otherwise dark, uniformly cratered surface, and its origin is uncertain. One hypothesis is that it represents a deposit of material with different composition, perhaps ice or frost condensed in this region, or material excavated from below the dark surface layer by the impact that formed the crater. The small scale of the feature and the limited resolution of Voyager 2's images have made it difficult to characterize definitively. Umbriel's overall darkness is itself interesting. The low albedo of its surface suggests that the dark material is not simply the dark rocky or carbonaceous material that covers many outer solar system bodies, but something produced by radiation processing, the transformation of surface materials by cosmic rays, solar wind, and ultraviolet radiation over billions of years. The specific composition of this dark material, which also darkens many of the smaller Uranian moons and ring particles, is not well characterized and would be a priority for future spectrometric observations. Titania is the largest of Uranus's moons, with a diameter of about 1,578 kilometers, making it the 8th largest moon in the solar system. It is also, along with Oberon, the most distant of the 5 major moons from Uranus. Titania's surface shows a varied geology, a mix of ancient, heavily cratered terrain and younger, smoother regions, with a prominent system of rifts and valleys crossing portions of the surface. The largest canyon system on Titania extends for over 1,500 kilometers, comparable in length to the East African Rift on Earth. These canyons indicate that Titania's interior expanded at some point in its history, possibly due to the freezing of internal water, since water expands when it freezes, or due to tidal heating driving interior differentiation, causing the surface to crack and pull apart. Titania has been suggested as a possible candidate for having a subsurface ocean today, based on models of its interior heat budget and composition. If Titania's interior contains sufficient radioactive elements to generate significant heat, combined with any contribution from tidal heating, temperatures at depth might be above the freezing point of a water-ammonia mixture, maintaining a liquid layer. Evidence from Voyager 2's limited flyby cannot confirm or rule out this possibility, and only future orbital measurements could constrain it. The discovery that several of Saturn's moons, Enceladus, Titan, and possibly Dione and Rhea, have subsurface oceans has led to renewed interest in whether the major Uranian moons might also be ocean worlds. Titania and Ariel are considered the most likely candidates based on size and probable heat budget, but uncertainty remains very high. Oberon is the outermost and second largest of the 5 major Uranian moons, with a diameter of about 1,522 kilometers, very similar to Titania. It has the oldest surface of the inner 5 moons after Umbriel, showing heavy cratering with few signs of geological resurfacing. Oberon's surface has one distinctive feature. Some of its large impact craters have dark deposits on their floors, darker material that appears to have welled up from below after the impact excavated the surface. This dark material may come from a layer of dark, carbon-rich material within Oberon's interior, exposed and redistributed by large impacts. If Oberon has a differentiated interior, a rocky core, possibly a liquid or slushy intermediate layer, and an icy mantle, impacts that excavated deeply enough might have brought material from the interior to the surface. Oberon was the last of Uranus's major moons to be observed closely by Voyager 2, and the flyby geometry meant that the images were taken at an oblique angle under lower resolution conditions than some of the inner moons. As a result, Oberon's surface is the least well-characterized of the five, with only general terrain types discernible rather than fine-scale features. The possibility that some of these moons may contain subsurface oceans has become more important in recent years. Ocean worlds are no longer considered rare curiosities. Europa, Ganymede, Enceladus, Titan, and perhaps several other icy moons have changed the way scientists think about liquid water in the outer solar system. Water does not need sunlight if internal heat, antifreeze chemistry, and tidal energy can keep it liquid beneath ice. The Uranian moons are smaller and colder than the most famous ocean worlds, but that does not automatically rule them out. Ammonia mixed with water lowers the freezing point. Radioactive decay in rocky interiors can supply heat. Past tidal resonances could have heated interiors during earlier epochs. A moon may not need a global ocean today to preserve evidence that it once had one. Fractures, resurfaced plains, relaxed craters, and cryovolcanic features can all act as surface clues. A Uranus orbiter could test these possibilities in ways Voyager 2 never could. It could look for induced magnetic fields caused by salty subsurface oceans. It could map surface compositions in infrared light. It could measure gravity anomalies during close flybys. It could image the unmapped northern hemispheres that Voyager never saw well. The difference between one flyby and an orbital tour is the difference between seeing a face in a passing window and studying a world. Together, the five major Uranian moons present a picture of a system with surprising geological variety. Miranda's bizarre patchwork terrain and towering cliffs, Ariel's rifts and relatively fresh surface, Umbriel's ancient uniformly dark crater field, Titania's expansive canyon systems, and Oberon's dark-floored craters all indicate that these are not simple, geologically uniform worlds, but places with complex histories driven by a combination of impact bombardment, tidal heating, and internal evolution. And all five are candidates, in varying degrees of likelihood, for having subsurface liquid water, making them potential ocean worlds in the outer solar system. The five major moons also give Uranus emotional weight as a destination. They are not just names orbiting a cold planet. They are landscapes. Miranda is the shocking one, small, broken-looking, and overcomplicated, as if a moon too small for major geology somehow found a way to build enormous cliffs and strange coronae. Ariel is the cleaner mystery, brighter and younger-looking, cut by valleys that suggest resurfacing and internal activity. Umbriel is dark and ancient, a moon that seems to have preserved the old outer solar system on its surface. Titania is broad and fractured, with canyon systems that imply expansion and deep internal change. Oberon is distant and old, cratered and shadowed, carrying dark deposits that hint at buried materials exposed by impact. This range matters for the viewer because it prevents Uranus from becoming only a planet of abstract physics. The system has places, cliffs, rift valleys, dark crater floors, possible oceans, ring shepherds, tiny moons moving in crowded inner orbits. A future Uranus mission would not only study an ice giant, it would reveal an entire miniature system of worlds that have been almost untouched by close exploration since 1986. The fact that the major moons are named from Shakespeare and Pope gives the system a strange literary quality, but the science beneath the names is serious. Miranda, Ariel, Umbriel, Titania, and Oberon may preserve different stages of icy moon evolution. Some may have been heated by tidal interactions. Some may have retained internal liquid layers for a time. Some may still hold briny pockets or deep oceans. Some may be frozen records of ancient activity. Without an orbiter, we cannot tell which story belongs to which moon. That uncertainty is not a weakness of the topic. It is part of the appeal. Uranus is not overexplained. It still has mystery left. The relationship between rings and small moons is especially important at Uranus because the system is compact and dark. The inner moons are close enough to one another that their long-term stability is not guaranteed in simple models. Some orbits may change gradually through gravitational interactions. Some moons may have collided in the past. Some may collide in the future. The rings may be debris from broken moons, and some moons may be rebuilt from ring material. The line between a small moon and a dense ring clump is not always permanent. This gives the Uranian system a quiet instability. Nothing looks dramatic on human timescales, but the architecture may be changing over millions of years. A small moon can shepherd a ring. A collision can create dust. Dust can spread into a faint ring. Ring material can be lost, darkened, or gathered. The system is not just a set of objects. It is a machine of weak gravity and slow consequences. That is why small moons matter. A 10-kilometer object may seem insignificant beside a planet 4 times wider than Earth, but in a ring system, a small moon can write structure into the dust around it. It can open gaps, maintain edges, seed particles, and preserve the memory of past disruption. When Webb finds or helps confirm a faint small moon, it is not merely adding a dot to the catalog. It is revealing another moving part in a system we barely understand. The inner small moons of Uranus, those orbiting within or near the ring system, are a collection of small, dark, irregularly shaped bodies that play important roles in shaping the ring system. Cordelia and Ophelia, as mentioned, shepherd the Epsilon ring. Cressida, Desdemona, Juliet, Portia, Rosalind, Mab, Cupid, and several others orbit in a relatively compact zone between the ring system and Miranda's orbit. These moons are too small to be spherical. They are probably lumpy, irregular objects ranging from about 20 to 100 kilometers across, and their surfaces are presumably dark and heavily processed by radiation, similar to the ring particles they interact with. Some of these inner moons are surprisingly close to each other and to the rings, orbiting in configurations that computer simulations suggest should be gravitationally unstable on timescales of millions to billions of years. They may be in the process of slowly colliding, reshuffling, or being tidally disrupted back into ring material. The whole inner Uranian system, rings and small moons together, may be a dynamically evolving environment where the boundary between moon and ring particle is not completely fixed, with material occasionally aggregating into small moons and then being scattered back into the ring system on long time scales. The irregular outer moons of Uranus, those in distant, often retrograde orbits far from the planet, are thought to be captured objects, either from the Kuiper belt or from the general population of outer solar system small bodies. They orbit at distances of tens to hundreds of times Uranus's radius, in orbits that are inclined and sometimes retrograde relative to the planet's rotation. These objects carry names from Shakespeare's darker works: Caliban, Sycorax, Prospero, Setebos, Stefano, Trinculo, and others. They are small, probably ranging from tens to perhaps 100 kilometers across, and dark, with nothing known about their surface compositions or internal structures. Voyager 2's flyby of Uranus in January 1986 remains the only close investigation the planet has ever received. The flyby was the third planetary encounter in the Grand Tour: Jupiter in 1979, Saturn in 1981, Uranus in 1986, and then Neptune in 1989, and it took place during one of the most peculiar moments in a peculiar planet's peculiar orbital cycle. Because Uranus was near its southern solstice at the time of the flyby, the planet's south pole was aimed roughly toward the Sun, and, given the alignment of Voyager 2's approach trajectory, also roughly toward the approaching spacecraft. This meant that as Voyager 2 approached Uranus, it was looking essentially down onto the South Pole. The rings appeared as nearly perfect concentric circles. The moons orbited in nearly face-on circular paths. The planet appeared as a disk with the South Pole prominently visible and the equatorial regions near the edge of the disk. This viewing geometry, while geometrically interesting, created some challenges for imaging and scientific investigation. The maximum resolution images of Uranus's cloud tops were obtained during the closest approach on January 24, 1986, when Voyager 2 passed within about 81,000 kilometers of the planet's cloud tops. At that distance, the cameras could resolve features a few kilometers across in the cloud layer, but the cloud layer showed remarkably little to resolve. The smooth, nearly featureless blue-green disk that Voyager 2 saw was unlike the dynamic, banded, stormy atmospheres of Jupiter and Saturn. This apparent featurelessness of Uranus's visible disk in 1986 generated significant discussion at the time. Some scientists attributed it to Uranus's lack of internal heat. Without heat rising from the interior, there is less convective energy available to drive the violent mixing and storm formation that creates Jupiter's visible banding. Others attributed it to the specific season, near solstice, with one pole in continuous sunlight and the other in continuous darkness for decades. The atmospheric circulation might be in a particularly quiescent state, suppressed by the unusual temperature distribution. And some suspected that the featurelessness was partly an artifact of the visible wavelength observations, that in near-infrared wavelengths, which can penetrate the upper methane haze layer and observe deeper cloud levels, the atmosphere would show more structure. The near-infrared suspicion proved correct. Subsequent observations of Uranus with Hubble, using instruments sensitive to near-infrared wavelengths, revealed clear cloud structures, bands, discrete clouds, and eventually storms that were invisible at visible wavelengths but present in the deeper atmospheric layers. The Voyager 2 cameras, operating primarily at visible wavelengths, had seen only the calm upper haze, missing the more turbulent atmosphere beneath. Beyond the planet itself, Voyager 2's most valuable observations were probably of the moons. The 5 major moons were imaged in detail for the first time, revealing Miranda's extraordinary terrain, the geological variety of the inner moons, and the ancient, cratered character of the outer moons. 11 new small inner moons were discovered during the flyby: Cordelia, Ophelia, Bianca, Cressida, Desdemona, Juliet, Portia, Rosalind, Puck, 1986 U9, and 1986 U10, bringing the known Uranian moon count from 5 to 16. And the rings were directly imaged for the first time, confirming the 1977 occultation discovery and revealing the Epsilon rings' shepherd moons. The magnetic field measurements from the flyby established the basic parameters of Uranus's unusual magnetic field: the tilt of 60 degrees, the offset from center, the complex multipole character. The magnetometer data has been analyzed in detail by planetary scientists over the subsequent decades, with increasingly sophisticated modeling. But a full understanding of Uranus's dynamo mechanism requires an orbiting spacecraft capable of making more extended and precise measurements. The Voyager 2 flyby lasted only a matter of days at closest approach, a brief, blazing passage through the Uranian system after years of travel. The images and data it collected were, in several cases, the only information we would have about specific objects for decades. Miranda, Umbriel, Oberon. Their surface character is known primarily from a handful of Voyager 2 images taken during a single flyby in January 1986. The entire scientific picture of Uranus that exists today is built primarily on that brief encounter, supplemented by decades of Earth-based and space telescope observations from hundreds of millions of kilometers away. No spacecraft has returned to Uranus in the 4 decades since Voyager 2's visit. That absence matters more than it might seem. Uranus is not simply waiting unchanged in a museum case. Its seasons are moving. Its atmosphere has entered a different part of its 84-year cycle. The North Polar region, hidden during the Voyager encounter, is now turned toward the Sun and toward our instruments. The ring plane has shifted as seen from Earth. Storms have appeared that Voyager did not witness. The system is offering a different face than it offered in 1986. A return mission would not be repeating Voyager. It would be visiting a different seasonal Uranus with better instruments, better questions, and decades of unsolved problems waiting for direct measurement. The question of future missions to Uranus has become one of the most actively discussed topics in planetary science over the past decade. The 2023 to 2032 Planetary Science and Astrobiology Decadal Survey, the comprehensive prioritization exercise conducted by the U.S. National Academies of Sciences, Engineering, and Medicine to guide NASA's planetary science program, identified a Uranus orbiter and probe as the highest priority new flagship mission for the decade, above even an Enceladus life detection mission and an orbiter at Neptune. The recommendation reflects a scientific case that has been building for years. Uranus is geologically, magnetically, and atmospherically one of the most complex and least understood planets in the solar system, and understanding it is directly relevant to understanding the most common type of planet found around other stars. The Decadal Survey recommended that a mission be developed with a possible launch opportunity in the 2030s, taking advantage of a Jupiter gravity assist that would be available in that time frame to reduce travel time to Uranus. A Uranus orbiter would also correct one of the deepest biases in our current knowledge, hemisphere bias. Voyager 2 saw the southern hemispheres of the major moons much better than the northern hemispheres because of the season and geometry of the flyby. Entire regions of these moons remain poorly imaged or essentially unseen at useful resolution. This means our geological understanding may be unbalanced. A moon that appears ancient on one side could hide younger terrain on the other. A suspected ocean world candidate could have fractures, deposits, or cryovolcanic features that simply were not visible in 1986. Repeated flybys would build global maps. They would turn Miranda from a half-known puzzle into a mapped world. They would show whether Ariel's resurfacing is global or regional. They would reveal whether Titania's canyons connect into larger tectonic systems. They would determine whether Oberon's dark deposits are local anomalies or part of a broader compositional pattern. They would let scientists compare all 5 moons under the same instrument suite and lighting conditions. The atmospheric probe would be just as important. The composition of Uranus's atmosphere is a direct clue to where and how it formed. If Uranus formed closer to the Sun and migrated outward, or formed in place from different planetesimals, the ratios of carbon, nitrogen, sulfur, oxygen, and noble gases should preserve traces of that history. These are not details that an orbiter alone can easily measure from above. The probe must fall into the atmosphere and sample the gas directly. The mission would also study the rings and small moons as a connected system. It could search for embedded moonlets, dust sources, ring waves, and subtle changes over time. It could determine whether the inner moons are stable or whether some are moving toward future collisions. It could watch the magnetosphere over many rotations and seasons, instead of accepting the one geometry Voyager happened to see. This is why the Uranus orbiter and probe concept has such strong scientific support. Uranus is not one question. It is a cluster of linked questions: impact history, interior structure, heat transport, magnetism, atmospheric dynamics, rings, moons, oceans, and exoplanet analogs. One mission could touch all of them. The proposed mission concept, The Uranus orbiter and probe would consist of an orbiter spacecraft that would spend multiple years studying Uranus and its system from orbit, plus an atmospheric probe that would be released to descend into Uranus's atmosphere and measure its composition, temperature, pressure, and wind structure at various depths before being destroyed by the increasing pressure. This two-element approach would address both the remote sensing objectives, mapping the surfaces of the moons, characterizing the magnetic field, studying the rings, and the critical in-situ measurement objectives that can only be achieved from within the atmosphere itself. The orbiter would make multiple flybys of each of the 5 major moons, building up the kind of comprehensive characterization that the Cassini mission achieved at Saturn's moons. Given the evidence for subsurface oceans within the Uranian moon system, and specifically the case for Titania and Ariel, the mission would specifically search for signatures of internal activity, magnetic field perturbations, surface features suggesting cryovolcanism or recent resurfacing, heat flow measurements from the surface. The detection of active geological processes on any of the major moons, or of evidence for subsurface liquid water, would dramatically expand the category of potentially habitable environments in the outer solar system. The atmospheric probe would address one of the fundamental questions about Uranus. What is the precise composition of its atmosphere at various depths? And specifically, what are the abundances of the key elements? Oxygen, carbon, nitrogen, sulfur, and noble gases that constrain models of how the planet formed? The bulk atmospheric composition measured from orbit gives limited information because the surface of the visible atmosphere represents only the uppermost layers. A probe descending to hundreds of bars of pressure, far deeper than the visible cloud tops, would sample atmospheric material that has mixed from the deep interior, giving a much more representative measure of the planet's bulk composition. This composition, compared to the Sun's composition and to the compositions of Jupiter and Saturn, would constrain the location where Uranus's building materials came from in the early solar system and what processes determined the planet's current state. A return to Uranus would also change how the planet feels culturally. Some worlds become real to the public only after spacecraft stay with them. Saturn became a living system because Cassini remained there for 13 years. Jupiter became a world of detailed weather, rings, auroras, and ocean moons because Galileo and Juno spent time in its neighborhood. Mars became a landscape because orbiters, landers, and rovers kept sending back surface images. Uranus has not had that chance. It is still mostly a single encounter from the 1980s. That is part of why Uranus is underappreciated, not because it lacks drama, but because no mission has given the drama time to unfold. A flyby can reveal a surprise. An orbiter can reveal a system. If a spacecraft spends years at Uranus, the story would no longer be limited to the sideways planet. The planet would become weather patterns, auroras, magnetic storms, ring arcs, moon maps, chemistry profiles, gravity measurements, and repeated close views of worlds now known mostly by names and half-lit Voyager images. The audience would finally have images and discoveries to attach to the science. Until then, Uranus occupies a strange place, scientifically urgent, visually underrepresented, and still waiting for the mission that will make it familiar. The development and launch of a Uranus orbiter and probe is still not guaranteed. It depends on NASA's budget priorities, political support for planetary science, and the outcome of competition with other proposed missions. But the Decadal Survey's strong prioritization gives it the clearest scientific mandate of any proposed outer solar system mission, and the preparation of detailed mission concepts, instrument designs, and trajectory analyses is well underway. A mission using one of the favorable 2030s trajectory opportunities could arrive at Uranus in the 2040s, roughly 60 years after Voyager 2's visit. There is also a human timescale problem. If a Uranus mission launches in the 2030s and arrives in the 2040s, Many of the scientists who helped argue for it may be late in their careers by the time the best data arrive. Some students who are children now may become the researchers who interpret its discoveries. Outer solar system exploration forces science to think across generations. It is not fast. It does not reward impatience. But the return can redefine a whole field. Voyager 2 did that with a flyby. Imagine what an orbiter could do over years. It would watch weather evolve instead of recording one moment. It would map the magnetic field through different solar wind conditions instead of measuring one passage. It would see moons from many angles instead of one hemisphere. It would follow rings over time. It would drop a probe into the atmosphere and measure composition directly. It would turn Uranus from a flyby planet into a studied system. An orbiter spending even 5 years at Uranus would accumulate more observational data about the planet and its system than everything gathered in all previous history combined. It would answer questions about the magnetic field, the interior, the atmospheric composition, the moon geology, and the ring dynamics that decades of Earth-based observation and 38 years of post-Voyager modeling have been circling without resolving. It is worth spending a moment on what Uranus represents in the broader context of planetary science and exoplanet astronomy. When the Kepler Space Telescope surveyed stars for transiting planets, it found that sub-Neptune planets, planets with masses between Earth's and about 4 times Earth's, are among the most common in the galaxy. Many of these planets, particularly those in close orbits, have compositions and densities broadly similar to Uranus and Neptune. They appear to be ice giant-like in composition, or intermediate between ice giants and rocky planets, with significant envelopes of lighter elements surrounding a denser core. This means that the ice giants of our solar system, Uranus and Neptune, each about 14 to 17 times Earth's mass, are somewhat larger representatives of a vast population of planets that are extremely common around other stars. Sub-Neptune exoplanets are found around at least 30 to 50% of Sun-like stars, and understanding them requires understanding what ice giants are made of, how their interiors work, what drives their atmospheric dynamics, and how they formed. Uranus is uniquely positioned as a study target for this class of planets because it is the only one we can study up close, or at least the only one we could study up close if we committed to a proper orbital mission. Neptune is similar but slightly less favorable in terms of travel time. The ice giants in other stellar systems are observable only as points of light, with bulk properties derivable from transit and radial velocity measurements, but with no possibility of imaging their surfaces, sampling their atmospheres, or measuring their magnetic fields directly. Everything we learn about Uranus's interior composition, its magnetic dynamo mechanism, its atmospheric dynamics, and its thermal structure adds to the library of physical understanding that planetary scientists draw on when interpreting the observations of distant ice giant exoplanets. The ice giant class, once considered a kind of embarrassing gap in planetary science, the 2 planets in the solar system least studied by dedicated missions, is now recognized as one of the most scientifically important categories, and Uranus as the closest accessible example. The problem is that most of those distant worlds can be measured only indirectly. We may know their size, their mass, and their orbital period. Sometimes we can detect molecules in their atmospheres, but we cannot see their winds, map their magnetic fields, inspect their moons, or drop a probe through their clouds. Uranus offers something those exoplanets cannot: proximity. It is far away by spacecraft standards, but close enough that instruments can eventually orbit it, sample its atmosphere, measure its gravity field, and fly past its moons again and again. That is why Uranus is not just a remote planet in our own system. It is a physical reference object for a whole class of worlds. A good Uranus mission would improve not only Uranus science, but exoplanet science. It would give models an anchor, one real ice giant with measured composition, measured interior constraints, measured magnetic structure, measured satellite geology, and measured atmospheric dynamics over time. There is something additionally interesting about Uranus's tilt in an exoplanet context. Planetary spin axes can be altered by giant impacts in the early solar system, and planetary systems in general are expected to experience significant large-scale collisions during their first tens to hundreds of millions of years. A planet tilted like Uranus, with extreme polar seasons and unusual atmospheric dynamics resulting from that tilt, might be surprisingly common among the exoplanets that form in dynamically violent early planetary systems. Uranus's tilt is not necessarily a cosmic anomaly, but might be a fairly normal outcome of the kind of large-body bombardment that many young planetary systems experience. Understanding what Uranus's tilt has done to its atmosphere, its interior thermal structure, and its moon system gives planetary scientists tools for thinking about the properties of distant, tilted ice giant exoplanets that currently cannot be resolved in any detail. There is something quietly remarkable about Uranus that doesn't come through in the numerical descriptions of its size, mass, tilt, and composition. It is remarkable in the sense of being genuinely strange. A planet that violates intuitions in almost every direction you look. The planet is tilted sideways. Its magnetic field is tilted 60 degrees from its axis of rotation and offset from the planet's center. Its atmosphere is the coldest in the solar system despite not being the most distant from the sun. Its interior apparently retains its heat instead of releasing it, for reasons that remain unclear. Its largest moon has a cliff 20 kilometers high. Its rings were discovered not by looking for them, but by watching what they did to a star's light. It was the first planet ever discovered through a telescope by a musician who thought he was looking at a comet. None of these things individually is impossible or even particularly strange in isolation. Giant impacts happen. Unusual magnetic dynamos exist. Cold atmospheres are explainable. But the combination, the accumulation of peculiarities in a single planet, makes Uranus stand out as a world where the standard models of planetary physics keep encountering surprises, keep producing predictions that don't quite match what we observe. This makes it scientifically interesting in precisely the most productive way. The surprises are data. Every aspect of Uranus that doesn't fit the model tells us something about what the model is missing, about what physics is operating in ways that haven't been fully captured. Working out what that physics is, what keeps Uranus's heat locked inside, what produces its unusual magnetic field, what tipped it onto its side, what drives geological activity in its small moons, whether liquid water hides beneath their icy surfaces, is doing science in the most direct sense. It's asking questions and looking for answers in the actual universe rather than in simplified theoretical constructs. The next spacecraft to visit Uranus, if the mission is finally approved, funded, built, and launched, will find a planet that has been waiting since 1986 with considerable patience. Its storms have come and gone in the intervening decades. Its rings have shifted their appearance as viewed from Earth. Its poles have turned toward and away from the sun, cycling through the 21-year seasons that Voyager 2 had no way to observe in real time. Its moons have continued their orbits, their surfaces unchanged in any way that 40 years of time without a visitor could change them. The universe, as a rule, is patient. Uranus will still be there, tilted on its preposterous axis, rolling through its 84-year orbit when the mission finally arrives. And when it does, this overlooked, underappreciated, strangely tilted planet will have a great deal to say. The next great Uranus image will probably not look like the Voyager image. It will come from a different season, with different lighting, different instruments, and a different scientific purpose. It may show a planet still pale and quiet to the eye, but surrounded by measurements that finally make the quiet understandable. That is the promise of returning. Not to make Uranus more dramatic than it is, but to discover how much drama was hidden behind the calm surface all along. By the end of a story like this, Uranus should no longer feel like the planet people skip. It should feel like a missing chapter. The solar system has given us detailed portraits of Mars, Jupiter, Saturn, and even Pluto. Uranus remains mostly a question mark with a pale blue-green face. That is not because it is unimportant. It is because it is difficult, distant, and patient. Uranus is still out there, blue-green and cold, rolling quietly through the outer solar system, its south pole and north pole alternately facing the distant sun in their 21-year cycles, its rings tracing dark circles in the darkness around it, and its moons carrying landscapes that no spacecraft has seen clearly since January 1986. It is easy to overlook a quiet planet. But Uranus is not quiet because it has nothing to say. It is quiet because we have not gone back to listen. And when we finally return, this sideways ice giant may answer questions that reach far beyond one distant world. How giant impacts shape planets, how ice giants form, how magnetic fields behave inside strange interiors, how small moons preserve oceans or lose them, and how common planets like Uranus may be across the galaxy. For now, it remains where it has always been, tilted, cold, distant, and unfinished in our understanding. It remains worth returning to. Good night.